Hi, let us continue from what we have left over in our previous videos. In the previous videos, we talked about a design example for a short column subjected to moment in both axes. Based on the moment given, we calculate the MED for the major and the minor axis. And then we do some checkings to determine whether the biaxial bending moment should be considered. The outcome shows that we need to consider the biaxial bending. Then our next step, it will be to determine which axis is more critical. This is determined by referring to the ratio of the moment versus the effective depth of that particular axis. We found that the minor axis is relatively critical than the major axis. Because of this, later the design of the reinforcement bar, it shall be on basis of the minor axis moment plus the effects due to the major axis. We use this formula to determine the design moment. Instead of using the calculated design moment in the minor axis, which is 14.1, plus the effects due to the major axis when the biaxial axis takes effect, it ends up to be the design moment equals to 23.9 kN meter. And then we determine the amount of reinforcement bar required based on the design chart. Finally, we came to the design reinforcement 4H16 plus 2H12. We haven't discussed about how the reinforcement bar should be arranged. Since now we are designing in the minor axis and we are providing 4H16 plus 2H12, that means the reinforcement bar should arrange something like this. The minor axis moment, it will be more critical. That means when we provide the reinforcement, we need to ensure the reinforcement are able to provide resistance against the rotations in the minor axis. 4H16 plus 2H12. None of the reinforcement bar should fall at the center of the minor axis. You have to be careful about the arrangement of reinforcement. Make sure you don't provide reinforcement in this manner. Arranging reinforcement in this manner, this will lead to this 2H12 be functional to the major axis but not functional to the minor axis. Now, if we are considering the resistance to the major axis, the total amount of reinforcement bar, it will become 4H16 plus 2H12. But if we look at the minor axis, the equivalent amount of reinforcement bar, it will only be 4H12. That means this arrangement is not applicable for this case, since the amount of reinforcement bar are determined on basis of the minor axis. Therefore, this arrangement of reinforcement bar should be applied. We also mentioned that having the amount of reinforcement bar determined, the calculation steps has not ended yet. There is one more step that we need to deal with, which is to fulfill the requirements of the Eurocode in terms of the design of the both axes. You may refer to clause 5.8.9 bracket 4. There is an equations that you need to check. This equations reflects the combined effect of the ratio, implying the capacity of that particular axis being used, both in the major and the minor axis. Multiply a factor A, which you can refer from a table, and the whole thing here need to be less than 1.0. Exceeding 1.0, that means the amount of reinforcement bar provided is still insufficient. Having this understood, we shall go through the relevant calculation steps. In order to adopt these equations, you will see the rationales of the equation is analyzing the capacity of the column in different axes separately. You need to get the MED versus the resistance of the moment in that particular axis. The calculations will be separated for the major and the minor axis. This brings to you have to do the separate calculations for the major and the minor axis. Now, how the reinforcement bar are arranged will be critical, especially the locations of these two H12. No doubt in the minor axis, the effective reinforcement bar it will be 4H16 plus 2H12. That gives you a total of reinforcement bar area 1030 mm square. However, when you are looking at the major axis, there will only be 4H16s to be effective. These two H12 falls in the neutral axis of the major axis. That means these two reinforcement bars are not functional in resisting the major axis moment. Therefore, we cannot consider the contributions of these two H12 in the major axis. This leads to you 4H16 plus no reinforcement bar in the major axis. The amount of reinforcement bar provided, it will be for the major axis only 804. As for the minor axis, you have 1030 mm square. Now you know the AS. Your next step now, it will be to determine the moment resistance in the major axis and in the minor axis. Knowing the amount of reinforcement bar provided, basically you can compute this as Fyk per BH FCK. Fyk, BH, FCK are the properties of the materials. These are given in the question. NED is also given, therefore we are able to produce this also. From the design chart, NED it will be the y-axis. The AS it will be the curve on the chart. By knowing these two, you are able to find out the moment resistance. Obtaining the intersections between the curve and the y-axis, you are able to determine the MRD. This is what we are going to do. Before that, we need to first determine the chart that we are using. You will need to calculate the D2 per H ratio. This represents the D2, which is calculated by the concrete cover plus the shelling plus half of the bar size. And then the H, it will be the height or the width of the column. Let's say this is the major axis. Then you are quantifying this D2 per H here. And then you will do the same for the minor axis. Get the D2 for the minor axis divided by the H. Now the H here, it will be the width of the column in the minor axis. Concrete cover equals to 35, which we have calculated earlier on. Shearing is 6 mm. Also we have calculated earlier on. And then the bar size is 16 divided by 2. Then you get the D2 for both axes divided by the H. For the major axis, the H it will be 300. As for the minor axis, the H it will be 150. That gives you D2 per H ratio equals to 0.163 and 0.327. We don't have the chart of 0.163 and also 0.327. On that basis, we shall refer to the chart with the D2 per H ratio closer to it. Let's say in this case, we choose to use the chart 0.15 and 0.25 for the major and the minor axis respectively. Now we're going to calculate the N per BH FCK. NED is given, which is 147.36 kilonewton. BH 150 times 300. FCK is given, grade 30. The axial load will be the same for both axes. That gives you 0.109. And then you need to determine the AS FYK BH FCK based on the actual amount of reinforcement bar provided. Substitute this 804 into the equation here. Multiply 500 divided by 150, 300 and FCK 30. You get 0.298. You will do the same again for the minor axis and it ends up to be 0.381. Now your next step, it will be referring to the chart in order to get your MRD. MRD stands for the resistance provided by the amount of reinforcement bar in that particular axis. Let us first deal with the chart D per H ratio equals to 0.15, which is meant for the major axis. Draw a horizontal line for N equals to 0.109, and then the curve AS FYK per BH FCK should be equals to 0.298. Refers to the scale here, as these scales are meant for this AS. 0.298 is close to 0.3. You find the intersections of this horizontal line and the curve here, and then draw a straight line downward from the intersections. That gives you 0.132. You will do the same for the other chart. This is meant for the minor axis. Draw a horizontal line for 0.109. And then you need to look for 0.381 from this AS curve. Refers to the scales here. 0.381 is close to the curve 0.4. You do some interpolations between the 0.4 and the 0.3. Draw a parallel line along the curve and it will intersect here. From the intersections, draw a straight line down and find the M per BH square FCK, which from the scale here, it is about 0.136. Having the two value obtained, the unknown, it will be the M. Let us solve the major axis first. Bring the BH square FCK to the opposite. This leads to 0.132 times B times H square and times FCK. You should be able to obtain the moment resistance of 53.5 kilonewton meter. You will do the same for the minor axis. Taking this as an equations, bring the BH square FCK to the opposite, multiply with 0.136. then theoretically you will get 27.5 kilonewton meter. You will have to be careful with the BH square here. For the major axis, the B it will be 150 and the H it will be 300. Since the dimensions of the columns is given 150 and 300. Now if you are dealing with the minor axis, now the B it will be 300 and the H it will be 150. Getting the wrong B and the wrong H will result in the wrong resistance of the sections. This you have to be careful. Now that we have calculated MRD, that means for these equations we have determined the MRD in the major axis and in the minor axis. Our next step is to determine the power of A. The power of A you will need to refer to this table. It is determined on the basis of the capacity of the axial load being used for that particular column. You need the NED and you need the resistance of the axial loads of the column. NED is given, which in these questions is 147.36. As for the axial resistance of the column, it is calculated as the summations of the capacity of concrete plus the capacity of the steel bar. The concrete area is calculated as B times H, which is 150 times 300. FCD is calculated from these equations. 0.85 times FCK, which is 30, divided by partial factor of safety of the concrete, which is 1.5. As for the AS, in this case we have two AS. You might be asking which to be used. You need to know the concept that we are calculating the axial resistance of the column. Axial resistance does not matter regarding whether the column is major or minor axis. As far as the axial resistance is concerned, all the reinforcement bar in the column should contribute. That gives you 4H16 plus 2H12. Your AS should be 1030 mm square. As for the FYD, it is calculated by having 0.87 FYK. FYK is given 500 Newton per mm square. Substitute the relevant value into the equations, you get your total resistance, axial load for that particular column equals to 1213.5 kilonewton. Your NED is 140 something. Divide the NED with the resistance, that gives you a ratio of 0.121. This ratio 0.121 refers to the table here. Interpolate it, you get A equals to 1.018. Now that you have the A as well as the moment resistance of the column in the major and the minor axis, your next step is to determine the MED, which is the design moment for the column in the major and the minor axis. In fact, the design moment for the columns has already been calculated previously. This MED for the major and the minor axis are calculated on the basis of the M02. Whereas, if you look at the equations for the M02, the moment due to the imperfections is incorporated. However, in the context of the moment subjected to bending in both directions, the effects of imperfections only goes to the critical side. The non-critical side, you may exclude the moment due to the imperfections. So, refers to the previous calculation step. M02 for the major axis is 27.4, whereas for the minor axis is 14.1. As for the moment due to the imperfections is 0.8. Take those numbers down. Next, you need to determine which side it will be more critical. Also, in our previous calculation steps, we know that the more critical side it will be in the minor axis. As a result, the effect of the imperfection shall retain in the minor axis, whereas the effects of the imperfections will need to be removed from the major axis. That gives you 27.4 minus 0.8 equals to 26.6. As for the minor axis, the M02 shall retain. After removing the moment due to the imperfections, we work out the new MED that you may apply into the equations here. Check against the M mean. The bigger value of the two shall serve as the MED for the major as well as the minor axis. With that, you have the MED in the major and minor axis. You have the A, which is equals to 1.018, and also you have the moment resistance in the major and the minor axis. Substitute into the equations and you get 1.0. The requirement is the calculated value cannot be more than 1.0, which in this case, your calculated value is equals to 1.0, which is acceptable. After completing this step, now you may confirm the amount of reinforcement, which in this case, we propose to have 4H16 plus 2H12 in the minor axis. Since that 2H12 falls in the neutral axis of the major axis, effectively in the major axis you only have 4H16. This shall be the layout of the reinforcement bar for this example.